So hey guys, this is the first video on the topic of the permutation group, or we can say the symmetric group. So permutation group, as the word suggests, the permutation means to arrange something. The sense of the permutation leads to the word arrangement. So what we are arranging here, this we will have to see. So by arranging something and then we will apply some the binary operation, then we will make the algebraic structure of group here. Yeah, so let's see how this group is formed. So since we have to do some arrangements, so for this let A be any non-empty set. So A can contain anything. For example, let A can be 1, 2, 3, any non-empty set, or A can be your some triangle, some square, some line segment, this, or A can be your say some happy emoji and say some sad emoji also. So A can be anything, just any non-empty set. A need not be finite, A need not be infinite. A just have to be non-empty. So for this, what we can do is we can define a new set as A. What does this set has? All those functions from A to A which are bijections, which are sorry, let me write like this, such that all those functions from A to A such and f is a bijection. It means in the set S A we are collecting all bijections on the set A. Now since we have the functions in the set S A, then the usual operation we can define on the set S A is the composition map. And now this form an algebraic structure, and this algebraic structure is the group structure under usual function composition. So what is the operation here? Operation here is between the two elements of SA. But how the elements of SA look like? They look like the functions on the set A. Not only just function, they are the bijective functions on set A. And what the usual operation we can give on the set SA is nothing but the binary operation, nothing but the composition function on the set SA. And under the composition function, this set becomes an algebraic structure, which is the group structure. This is the way we define the permutation group. So why we need the permutation group, we will see in the later. Now for example, let us see that, suppose for some example, let take A is equals to some 1 comma 2, or we can assume some B is equals to some triangle, some square like this, or we can assume C is equals to some this sad emoji and some this happy emoji. Then we have SA, we have SB, and we also have SC. Now SA is those functions which are from A to A and bijective. Similarly, this SB is nothing but all those functions which are on B and bijective, and same for C, and same for C similarly. But since this is just any two set of cardinality 2, B is also any set of cardinality 2, C is also any set of cardinality 2, and SA and cardinality of SA is equals to cardinality of SB is equals to cardinality of SC is nothing but 2 factorial, which is equal to 2. It is very trivial to check number of bijections on a set, on a finite set A whose cardinality is n, then its answer will be n factorial. Similarly here, since there are only two elements in set A and set B and set C, The number of bijections on A, B, C are 2 each. So, but these groups are isomorphic. It means that we don't need to discuss we do not need to discuss this SA, SB and SC in the different fashion. Once we have the once we have the same finite cardinality of the chosen set A, B, C, then we do not need to discuss their corresponding symmetric group in different fashion. If I have discussed the SA, then I have also discussed the SB and also I have discussed the SA. So in this matter, what we will assume that we will take the classical thing that either A looks like 1 to up to n, or A looks like A1, A2, some an. If I have to say the cardinality of A, then what will I say that A either looks like 1 to n, or A either looks like A1 to an. So in this way, we fix our chosen set A. We will never take some this type of set like B, like C. We will make the things very simple so that we can work on this group. Okay, so let's see some example. Okay, one more thing, that it need not be true. Let me write it here. It is not required to choose A to be finite. We can choose A to be infinite set also. Infinite set also. And then we can define SA. So it is not required to choose that A should be the finite set. We can still define the symmetry group over any infinite set A. Okay, let's see some example. If I am saying that cardinality of A is 3, then by default I am assuming that A is equals to 1 comma 2 comma 3, or I am assuming that A is equals to A1 comma A2 comma A3. In the 99.9% case, I will choose that A is equals to 1, 2, 3. If I do not mention that how the A looks like, then we will by default assume that A is of the first class. It means A always looks like 1, 2, 3 up to n if the cardinality of A is n. Okay, since we have the cardinality of A is 3, then what we have SA. Now we will introduce a new symbol for SA as per cardinality of A. This is done only in case of finite, provided that A is finite. This new symbol is used only when the A set is finite. And how is the new symbol defined? If cardinality of A is n, then we replace SA by Sn, and we are assuming that A how looks like? A looks like the earlier way we defined. Okay, so this is our notions and convention. So now under this notion and convention, if I have to define the S3, then what does this S3 has? F3 has those functions which are from 1, 2, 3 to 1, 2, 3 and bijective. So this is the set. So how will the function look like? Clearly, so what we have, we can make elements like this. We have the 1, 2, 3. 1 can goes to 1, 2 can goes to 2, 3 can goes to 3. This is one function. Is it clear? Yeah. So one function is, then the second function, what we can do that we can fix some element. Say suppose we fix 1. 1 goes to 1, 2 goes to 3 and 3 goes to 2. Now suppose we fix the second element 2, then how we can define? We can define like 1 is fixed, sorry, 1 is not fixed, 2 is fixed, but 3 is not fixed, like this. And we have to maintain the bijectiveness also. And similarly, we can fix 3. And how we will write? 1 goes to 2, 2 goes to 1, 3 goes to 3. Now, what else we can do? We can shift by the 1 index. 1 goes to 2, 2 goes to 3, and 3 goes to 1. What else we can do? We can shift by the index 2. So 1 goes to 3, 2 goes to 1, and 3 goes to 2. These are the all 6 elements. We can only make these 6 elements. You can easily check. Obviously, that the number of bijection on a set A with cardinality n has to be n factorial. Here, since n is equals to 3, we can only get the 3 factorials. And these all are the 3 factorials which I have written. And these are the only which we will get. So this is my set S3. This is set S3. Similarly, we can construct the set S4. And what will the cardinality of S4? This is 4 factorial. Okay, in the coming videos, we will analyze more about this group, permutation group Sn. For now, let me tell you why this permutation group is important. The need of permutation group. Need of permutation group. Permutation group. So the need is the following. That then what is the need? Need is because of the Kelly theorem. Because of because of Kelly's theorem. What does it say? That any finite group of cardinality n is embedded in a Sn. So this is the definition of the Calais theorem. So sorry, this is the statement of the Calais theorem. So as per this definition, it is saying that we can embed any finite group in some permutation group. It means that if we study the permutation group, if we study all types of permutation group, it means we study S3, S4, S5 up to so on, then we are actually studying all types of finite groups also. Because this Calais theorem says that any finite group of cardinality n is embedded in a Sn. It means that a there exists an 1-1 map. Suppose that the group is G and there exists a 1-1 map from G to Sn such that the map is homomorphism. So this is the statement of the Calais theorem. So this is very important theorem, and because of this Calais theorem, we have to study the permutation group. Why? Because once we study the permutation group, the other task of studying the finite group is also done by us. So this is the just general introduction about the permutation group. We will analyze this group in a detailed manner in the coming videos. So thank you so much.